All right, guys, kind of a quick video today. Unit 7C, we're talking about the law of large numbers, which is something that we've brought up in class already. If you remember, we were talking about flipping a coin, and we said, what is harder to do? Is it harder to get 9 out of 10 heads? So is it harder to get heads 9 times out of 10? Or is it harder to get 900 heads out of 1,000 flips? And a lot of you in the beginning had said, well, 9 out of 10s is harder to do than 900 out of 1,000. But when you start to think about the 900 out of 1,000, that's getting 9 out of 10 100 times. You've got to get 9 out of 10 over and over and over and over again to end up with 900 out of 1,000. When really we know that we're more likely to get heads 1 out of 2 times, about 50% of the time. Now, the law of large numbers says that if I'm considering an event with a probability, the law of large numbers says that the more I try this, the more trials that I do, the closer I'm going to get to my theoretical probability. Okay? The closer I'm going to get to my theoretical probability. So the larger number of trials, the closer my proportion should be to my theoretical probability. Now, this holds true as long as each of these independent trials, or as long as each of these trials is independent of the other trials. Okay, so down here you've got kind of a diagram of somebody rolling a dice. Now, they obviously didn't roll the dice 5,000 times. They used a computer program, but in the beginning, the probability of getting a 1 is 1 out of 6 chances. So you expect right here, 0.167. And the first 500 rolls, the probability is a little bit low. It's at like 0.15. So this is like 0.148. So it's a little bit lower than 0.15. And then all of a sudden at 1,000 rolls, we kind of peak and get over the expected probability. But as the rolls go, if you look right here, we're kind of bouncing around a whole bunch. But as we get bigger and bigger, once we start getting to 2,000 rolls, 3,000 rolls, 4,000, 5,000, look at how much closer I'm getting to my expected probability. I'm getting closer and closer and closer the more trials that I do, okay? So how that works in our math class. So of course, this is exciting math, so we get to talk about gambling and roulette. So as shown at the left, so a roulette table is the game at casinos where they drop a ball and this thing is spinning around and the ball bounces around and flops and flips and it ends up landing in one of these different little chunks of the table. So there's 38 numbers. 18 of them are black, 18 of them are red, and then there's 2 green ones, a 0 and a 00. Now, if we assume that all the possible outcomes have an equal probability, okay? So we're going to say it's just as likely to get this 0 as it is to get a 7, as it is to get a 12. Those are all just as likely to happen. So what is the probability of getting a red number? So if I spin one time, I've got 18 red numbers out of 38 total numbers. So that's my probability, 18 out of 38. Now, we should probably simplify this to be 9 over 19. So I've got 9 out of 19 chances of getting a red. That's my probability. So if patrons in a casino, if they spin the wheel 100,000 times, about how many times will a red number be the outcome? Well, if I spin 100,000 times and I expect this probability for each spin, all I'm going to do is times that by 100,000. So we're going to take 9 over 19, and we're going to do that 1,000 times, or 100,000 times. So I expect to get red 47,368 times. And I guess there's a 0.421, but This is kind of what we're talking about, right? So that's how many times you would expect to get red. That's our expectation, especially if you do it 100,000 times, you're going to get really, really, really close to that actual probability. Even if your first 50 spins are black, by the time you do this 100,000 times, you would expect to be close to that number of reds. All right. Now, our expected value, if we're considering two different events, our expected value, you take the value of event one happening and you times that by the probability of the event happening. And then you're going to add that to the value and probability of something else happening. So for example, lottery expectation. Suppose that $1 lottery tickets have the following probabilities. You have 1 in 5 chances to win a free ticket worth $1. So you have 1 in 5 chances of winning $1. You have 1 in 100 chances of winning $5. And you have 1 in 100,000 chances of winning $1,000. And you have 1 in 10 million chances, 1, 2, 3, 1, 2, 3, of winning $1 million. What is the expected value of a lottery ticket? So if these are all of the values and all of the probabilities, we take the value, times it by the probability, and then we're going to add all of these together. So the chances of winning a dollar ticket are 1 in 5. The chances of winning a $5 ticket are 1 in 100. So we're going to times those and add it to these times together and add it to these times together. And then we're going to add that to these times together. But there's one that we forget. We have to add the fact that we are buying a ticket, because that's also part of this process. So I have a 1 in 5 chance of winning $1, but I have a 5 out of, and how should we write this? Let's just say a 1. I have a 100% chance that I'm going to spend $1. So I can't just look at the probabilities of winning. I have to add the probability of that dollar that I actually spent. I have a 100% chance of spending $1, and then I add all of these probabilities of winning something back. So on my calculator, I've got 1 times -1. That one's easy, right? That's this last one right here. I usually do that one first. I usually do my spending probability at the beginning. And then I'm going to times 1 out of 5 chances of winning $1. And then I'm going to add my 1 out of 100 chances of winning $5. And then I'm going to add my 1 in 100,000 chances of winning $1,000. And then I'm going to add my 1 out of 10 million, 1, 2, 3, 4, 5, 6, chances of winning $1 million, 1, 2, 3, 4, 5, 6. So I'm going to add all those together. And what that tells me is, let's see, 1 times -1, 1/5 times 1, 1/100th times 5. Let's make sure I put all of these in correctly. Nope, that's not what I wanted. Let's go back up here. 1 times 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay, so my expected value is going to be negative. I can expect to lose 4 cents. That would be my expected value. I would be expecting to lose 4 cents. Now that doesn't sound right. Let's see. Oh, there it is right there. That's supposed to be a plus. Okay. I'm going, man, if that's all you're losing on a lottery ticket, then we've got an issue. There we go. That sounds more correct. We are expecting to lose 64 cents for every lottery ticket. I accidentally put a multiplication right here instead of a plus. So be careful of that. You add all these together. So you're expected to lose 64 cents on each ticket that you buy, which is how the lottery makes money, right? Even though there's all these chances of winning, most people are losing 64 cents on their dollar. So at an art auction, you're trying to decide whether to bid $50,000 for a painting. Well, if I were to buy this painting for $50,000, that is, I've got a 100% chance of losing $50,000. That's going to happen, right? But it says that you believe that you have a 1 in 2 probability of reselling the painting. So you have 1 out of 2 chances of selling it for $70,000. And you have a 1 out of 4 chances of selling it for $80,000. Otherwise, you have to keep the painting, an option that has benefits but not monetary ones. What's the expected value? So my expected value, I know that I'm going to spend $50,000. That's guaranteed. But I have a, oops, I did it again. That's a plus. I have a 50% chance of selling it for $70,000. Now talk about, this is subjective probability, right? You believe that you have a 1 in 2 probability. So you think you have a 50% chance. Hopefully your intuition is strong on this one. And then you have a 1 in 4 chance of selling it for $80,000. So what is your expected value? Your expected value would be $5,000. That's the expected value if you are to invest $50,000 on this painting. That's the expected value, okay? All right, moving on. Out of expected value. Not the most interesting stuff, but this is the gambler's fallacy. The theory really gets people in trouble. So consider a simple coin toss game where you win $1 if you get heads and you lose $1 if you land tails. If you toss the coin 100 times and get 45 heads and 55 tails, that means that you won $45, but you spent $55. So that means you're negative $10 in the hole. You owe $10. Are you due for a streak of better luck? Now, theoretically, as this game goes on, you should be getting closer and closer to 50-50 chance, right? And obviously, you're close to 50-50. 45 heads instead of 50 heads, that's pretty close to a 50% success rate. But obviously, the answer is no. Just because you have had some bad luck doesn't mean that all of a sudden it's going to change, okay? Every time you flip the coin, you have the same chance of getting heads as you did the time before. It doesn't matter how many tails you got in a row. You could have had 20 tails in a row. You still have the same chance of getting heads as you did every other flip of the coin, okay? But there's this gambler's fallacy that believe I've had a whole bunch of bad luck, but because I have a 50-50 chance, all of a sudden, I'm going to have a good luck streak. Now, I want you to think about this situation, okay? So if you're playing this coin toss game and you win $1 for heads, you lose $1 for tails. So after 100 tosses, you're $10 in the hole. So you've gotten 45 heads and you've got 55 tails. So what that means is really you are only 5% off of the expected value. You're only 5% off. So you owe $10, okay? So let's say that you play this game 1,000 times. Now, the law of large numbers says that as you get closer and closer to 1,000, you should be getting closer and closer to that 50%, okay? So you flip a 1,000 coins and you get 480 heads and 520 tails. So if you have 480 heads and 520 tails, now you are at 48% heads. So you're only 2% off of being perfect, 50-50. But here's the problem. Now that you're at 480 and 520, now you owe $40 or $400. Now you owe you owe $40. So even though you get closer to that 50-50, your number of bets have gotten a lot bigger. And here's where the gambler's fallacy gets them in trouble, okay? You might be 10% off after 100 bets. After 1,000 bets, you might only be 1% off, but you are 1% off of 1,000 bets. Okay. So even though you're closer to the 50-50, you're 1% off of a larger number. So you're still in the hole. So this person, now they're at 48% success. They're closer to 50, but they owe more money. They haven't come out ahead. Now they owe $40 instead of just $10. So you've got to be really careful with this law of large numbers because it's true. But the more you bet, the more number of bets you have, the higher, even though your percent is lower, that is a percent of a larger number. So you might still be losing a lot of money. Planning for the rain. So a farmer knows that at this time of year, the chances of rain is 50%. It has not rained in 10 days, and he needs to decide whether to start irrigating. Is he justified in postponing irrigation because his region is due for a rainy day? Now, this theory, this idea that, okay, I should have 50 rainy days out of 100 days, and I've had 10 days in a row without rain, so I'm due for a rainy day. This is a scary theory because even though it feels like that with the law of large numbers, that day you still have a 50-50 chance of rain. It doesn't matter if you've had 50 days in a row without rain. You still have a 50-50 chance of getting rain the next day. You are not any more likely to get rain because you've had a 10-day streak of no rain, if this probability is equal from day to day, right? Okay, that's it for today's video. I told you it was a quick one. So homework, now we are on 7C. One more homework, guys, and we're already reviewing for the next test. So homework 7C, do what you can at home, but we will be going over this one in class. We'll spend some time on the homework, answering questions, and expanding on these ideas a little bit.